All right, let's go ahead and get started. Where we left off on Friday is kind of the end of this topic, just labeled as variables, and I wanted us to go through this problem-solving exercise. We kind of ran out of time on Friday, and now it's Wednesday, and I'd like us to get to it today. This also goes through the kind of questions I tend to see, or the TA tends to see, which is you're given a new program to work on. You're given a lab assignment, part 3 of lab 4 or something, and oftentimes the hardest part is just knowing how do I get started? What should I do when I'm just faced with a blank editor and I don't really know how to even begin on a problem? And part of it is I don't know if there's a straightforward way that you've learned that from not knowing that. I think we learn that just through practice, just through being faced with different variety of problems, and just in different environments, whether it's a classroom environment, whether you're in the lab environment, or whether you're just off then by yourself, just kind of facing a challenge, facing a problem, and just kind of working your way through it. And for me, this is just my approach, and this is the approach I'd like you to consider. I really like the idea of not just diving into code immediately right away, but pencil and paper, or in this case, we'll just have a notes page, notes tab kind of open here, journaling down your thoughts before you worry about what your actual C syntax is going to look like. For the most part, if you can write down your thoughts, if you can have a coherent thought as to what steps make sense, you will be able to figure out the code as you go. We're a little limited in terms of the type of programs we can still do at this point in the semester, but I think we can handle this particular problem-solving exercise. Where we were talking about on Friday was we have different ways of representing even integer values, and we talked about different number systems, and we didn't go into too much depth about binary and hexadecimal, but we did talk about the base 10 number system. And for this example, this would be a program whose goal is to take as an input an integer value, and then to return as output the sum of that integer's decimal digits. So with an example here that if the input was 257, then the output should be 2 plus 5 plus 7, or the output would be 14 in that case. So for me, given that challenge, I look at that and I say, well, I don't necessarily know where to begin. I start by just beginning to journal my thoughts along the way, where, okay, my goal to sum an integer's decimal digits. Which, okay, is fine. That's just our starting goal, to sum an integer's decimal digits. Fine. When we were looking at this for our very first problem in the first week, we kind of broke it down into the problem specification to begin with. Now again, the problem specification is given here. It's not always going to be given in such a clean, straightforward way, but at the very least, we should be breaking down what are our inputs, what are our outputs. In this case, while we could have the input be something like a string of digits, and that would kind of change the nature of our solution, here it's given more explicitly as being an integer value. And at this point, if you'd like to, you could name it if you'd like to. You could call this input value. You don't have to necessarily name it at that point, but you certainly can. And output, another integer value, representing the sum of the digits of input value. What's not exactly given here, and it's always one of the questions you then have to ask yourself when you're trying to solve a problem, is always the specification is either ambiguous or it's vague in some aspect or the other. There has to be some reasonable limits or constraints. It's not given as part of the problem. It's the question you have to ask. Okay, does this have to work for any integer of any particular size? You could call this assumptions. Input value, and let's just say for now is in the range 0 to 100 would be fine. Let's do 0 to, because 257 was the example, between 0 and 512. I didn't provide that there. I didn't say assume it's within that range. But to solve our problem, we always have to make some simplifying assumption or some assumption that says, okay, under what possible infinite space of the problem am I solving? Well, what's a reasonable constraint? And then that becomes a negotiation. Is that a valid constraint? If I assume input value is always 0, then that's also technically a constraint, but it's not, then the problem is kind of not very interesting anymore here. Here we have a constraint of input values in the range 0 to 512. It's still an interesting problem. If we want to handle any arbitrary input value, we can probably still do it. It's just the code would be a little bit more complicated. So we put a reasonable constraint in there and we hope that that's going to be fine. So in terms of problem analysis, and we go back to, if the input is 257, then the output should be 2 plus 5 plus 7 or 14. Another way to think about that problem analysis is kind of just repeating what the problem is. We are to be summing an input's decimal digits. My spelling is not wonderful today. So need to get an input. You may not be there yet, but very soon that should be like, I know I'm going to need my scanf and maybe my printf little muscle memory of grab some input from the user, right? Okay, I know I need to get that input. Need some mechanism to obtain an individual decimal digit. Need to calculate the sum of the digits. That one I think we could probably figure out, or we have like the plus operator. Okay, so we know there's gonna be some plus operation going on in here. Okay, and again, that doesn't necessarily give us our answer yet because now there's still an unknown. Some mechanism to obtain an individual decimal digit. Further thought, assuming the input we should be calculating 2 plus 5 plus 7 equals 14. That's given in the problem, but that's our further analysis. That's our example of what it should do. Sure. You should be writing your own notes. This is just quick thoughts and notes that we have here. I could provide this file if you actually need it. I think listening is probably sufficient for this as well, because you're not going to have to go back and implement this also yourself. But the thought process is what I want you to get some more exposure to here. So calculating the 2 plus 5 plus 7 equals 14. Okay, calculating 2 plus 5 plus 7 is straightforward, I think. How to get to 5, 7. And these are kind of internal journaling and notes, right? This isn't like a formal thing that you're submitting here. How do I get that 2, then 5, then 7? I think it's a valid assumption to make, at least in the academic context of being inside a classroom here. Okay, how do I get that 2 and that 5 and that 7? Have we learned anything that would allow us to do that? Because, otherwise, of course, the space is very large of possible things one can use. In general, at least my goal is, I provide you a problem, I give you a lab or other assignment, I expect that you're able to figure it out with what we've been covering either in class or in your reading. So that's also kind of a hidden, call it an academic constraint that may not be there in other problems you work on in life. But in EE285, that'll be another constraint. You should be able to solve the problems with the tools you have learned to this point in the semester. So for us, that would actually mean we haven't covered ifs and for loops. A lot of you have that background, but that's probably not necessary here. There could be ways to solve this that involve looping structures and things like that. That would potentially be a valid thing, but it's actually not necessary for this problem. Given this constraint of the value fitting in that range, there's a limit to how much arithmetic is required for this particular problem. In terms of an algorithm, this doesn't necessarily answer the question yet. We don't quite have an answer yet. So we have assuming 257 is our input. Is there a mechanism by which we can take 257 and get back out, for example, 7. Or 2. We could do it either way. Is there an operator that, given 257 as an input, returns 7? The remainder operator. Remainder what? How can we do it with the remainder operator? Yeah, absolutely. So if we talk about our algorithm here, so we can still think, read in input, that's fine. Grab, I would call it the least significant decimal digit, which would input value mod 10 or remainder 10. That remainder operator, and this is one of those programming tricks. If you've seen it before, it's so obvious, and if you haven't seen it before, well, now you've seen it. So now you see it for all future examples. If our input value is 257, we calculate the remainder when we've divided by 10. That's what that modulus operator does. Well, that value is going to be in the range 0 to 9. The remainder when we divide by 10 is going to be 7 if our input was 257. We have then gotten that digit. We're not quite done because now we have to kind of get to the next digit. What else can we do? We have 257. We've grabbed 7. What else can we do? We need to get the next 2 digits as well, right? I would say something like, we grab least significant decimal digit. We can also then kind of shift the decimal value so that we've gotten rid of the 7. And we can do that by taking input value then divided by 10, which our rules for integer division allow us to say, if I take 257 and divide by 10, we don't actually get 25.7, right? We saw that last week. We take 257, we divide by 10, we actually get 25 back out, to get 7. Just to give this more example here, to get 25. I don't know if saying e.g. each line is the right way to do this, but at least it's again, still kind of journaling our thoughts here, right? So we started with, we grabbed 257. We can get the individual digit 7. We can then shift that decimal value. We're missing one more step here, and that's really all it is. What's the additional step for this problem? Well, you have to kind of, I would say maybe there's more than one step, repeat until done. And eventually we'll learn about looping structures, repetition structures that allow us to, a relatively small amount of lines of code, repeat the rest of what we've already done. In this case, we don't have to repeat too many times. If our value is in the range 0 to 512, 3 times should suffice for this problem. But there's one more thing we actually have to calculate. So if we're going to call that step 5, there is another step 4. We've grabbed the digit 7. We have to do something with the digit. You have to save it, absolutely. And this doesn't describe the intermediate variables. We still have to write the program. We have to also calculate the sum as well, right? The sum of the digits. Sum, add digit to sum. You could argue, I think that's valid to say, if you do it afterwards, it should still be fine. That we should probably do that before we shift it over to the right. Now, what have we not done yet? We've not written a single line of C yet. And frankly, this is kind of my shorthand, kind of thinking it through based on your feedback as well. If you were to start that completely from scratch and go through this process, it's totally fine and natural that your notes look a little different and you phrase things differently, or you've just solved the problem differently. That's obviously perfectly fine as well. But you're way better off having some thought process versus just having no thought process and just having an open blank .c file and just hoping that magically you'll work your way through it just by typing stuff until eventually something compiles and then debugging that. This does not answer the question. We don't have a successful working piece of C code yet. But with this here, both the problem analysis, I would say, as well as the algorithm, eventually you'll get pretty good and eventually meaning like this semester, in going from this kind of pretty high level, very informal way of viewing what your code is supposed to do, you'll get pretty darn good at going from that to then your actual C code. It may seem unfair when I do it in class because I'm just typing really fast and everything just kind of magically works the first time. That's fair, but eventually you'll also get very good at that. It's easier for me. Okay, I've done this problem before. I've done these problems many, 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 many times. But that is really what it means to be a programmer. Understand that you have a problem to solve, breaking it down into specification. Sometimes it's an academic specification, other times you have some actual real work to get done. Breaking it down into a set of logical steps, given a set of constraints and other assumptions, and then, and I would say only then, worry about what does this mean from a programmer's perspective. And I think, just for this example at least, we can implement this pretty quickly. This is example print digits in our just lecture replets here, and it is in fact quite blank currently. We had specified that we may have an input variable called input value and an integer value representing the sum of the digits, which we didn't give a name to. Digits, digit sum, it doesn't matter. Sum of digits, whatever you can remember what it's called after the fact. Okay, so an input's going to be an integer value called input value, and there's an output, an integer value. It's not a bad idea to declare those first thing in your program. I've already said they're integers, but now we know we're declaring them as such. You can initialize them. You don't have to necessarily initialize them for at time of declaration. For an input value, we oftentimes don't feel the need to initialize it at declaration time because we know the very first thing our program is going to do is it's going to read in that value. I'm going to include these as comments. I'm not saying necessarily you would always necessarily want to do that, but this is just to kind of show the direct connection between what we wrote in that notes page and then what our code is going to look like. Read in an input, for example, 257. It's valid to say, hey, let's not worry about reading an input. If you want to test your code, feel free to hard code it to start with. There's always some trade-offs involved in hard coding your input versus actually reading in different inputs. The risk sometimes is like you write a program that only works for that one particular input because you haven't fully thought through all the different potential issues here. But the trade-off is, it's easier to write a program that only works for 257, so you can kind of build from that. I think we need to really get into the habit of our kind of printf, scanf kind of prompt process, where we're going to use that scanf using that ampersand that we've kind of hand waved away so far this semester to grab that. It's nice to have a printf. So please, always ask your users, please enter in a value, an integer value, I guess, integer value in the range that we specified for this problem. And I like a little, colon afterwards with a space. Please enter in an integer value in the range 0 to 512. Scanf with that scanf that your code's never going to run right if you didn't do the scanf correctly. I'm still a fan and a fan of you immediately printing out that value, at least temporarily. You entered in that value with a little new line at the end there. Code doesn't do anything yet. We can at least test it. When I type in 257, it said you entered in 257. Okay, it doesn't do anything yet, but at least it's something here. We probably then can get rid of that little printf for now. No harm, we just comment it out. We have read in the input. Grab least significant decimal digit, input value mod 10. To get a value of 7, we probably at this point then need to declare another variable to kind of store that digit. We didn't come up with a name for it. In C, and this is not true of like even older versions of the C standard, but certainly today you can declare your variables essentially wherever you want. So it is perfectly valid to say int digit, which would be a new variable, is input value mod 10. There's nothing wrong with that. I kind of like declaring them all at the beginning of the function. It allows me to kind of very clearly specify, okay, here are the variables I think my program is going to need, and I should expect that they're all going to be used inside that function. But declaring it on line 16 would have also been satisfactory to do so. Digit equals input value mod 10. Not to belabor the point, but I'd say, hey, we just added some math. Let's print it again. For us, that's mod 10. Least significant digit is this value we just calculated, and let's print it out. Okay, I don't know why I have to click 30 times, type 257. Least significant digit is 7. We did 257 mod 10. We did get a value of 7 back out. That is our digit here. We then have to then take, what's the next step here? Add digit to sum. Let me copy all these in here so we have them. Add the digit to sum. We have a variable that we call digit sum, which just sounds awkward, but it is what it is. We have to add it to the existing sum plus the digit. This is actually technically a bug that we've added in our code here. We take the current value of digit sum, we add it to digit. In that case, we do need to be a bit more explicit and say, hey, this is a running sum. We haven't really initialized it anywhere else. Replit may kind of paper over that bug for us, but in practice, let's initialize it. Let's make sure it actually started at 0. Then that first time through, we've added 7 to it. We get a current running sum of digit sum. Shift the decimal value so that it's that value divided by 10 to get to 25 from our 257. Should look pretty similar. It's input value we want to change. Kind of repeat until done. Do it 3 times in total. And then I'm going to get rid of the comments here because they're repetitive comments now. Grab another digit, grab the 5. Add it to the sum, divide again. Grab another digit, add it to the sum, divide again. If our value is in the range 0 to 512, we are guaranteed that there's 3 or fewer decimal digits. What happens if the value was just 19 and only had 2 decimal digits? In this instance, because we're calculating the sum, there's really no harm. What is 0 mod 10? Well, it's 0. So we just keep adding 0 to the sum multiple times. It doesn't change the result is still correct. So whether we actually need to do it 3 total times or not is a function of what our value is, if it requires 3 digits or not. There's no harm, at least in this implementation, in always doing it 3 times, even if we really only needed to do it twice or 1 more time. And I didn't really give it as part of the algorithm. We really should, print out the value. The sum of the digits of our value is this value. That is another bug, but we will fix it. Type in 257. The sum of the digits of 0 is 14. That's not quite correct, right? Because we were modifying input value as we went. We could create a second input value if we're worried about that. So we could do something like, okay, we've grabbed input value. There's more than one way we could change it. We could just call it, current value. And we could do current value instead. I just did it like a find replace. I said, okay, we have this input value. We actually want to hang on to it only for printf purposes. So this one should not be changed. So I just created a copy of it basically. Saying, okay, we grabbed input value. Let's create a copy of it, call it current value, just because I wanted to print out the input value. Whereas this code otherwise is changing that value because it's dividing it by 10, which is why we got the sum of the digits of 0 is 14. That's not correct. Now if we do that again, we'll be printing out the original input value, and now we get the printf that is correct. The sum of the digits of 257 is 14, which is correct. You know, we should test it with more than one value. I don't know. Sum of the digits of 101 is 2. It's something that eventually you learn in more software engineering focused classes, which is, what is the right amount of things and how do we truly know our code is working or not. For the purposes of this class, we give it a few reasonable values. We run it, we get a result that seems correct. That's sufficient for our purposes. Eventually, once you already become very adept at programming, then we kind of treat testing and verification as its own separate engineering practice that we have to worry about, which is how do we provide real confidence that the code that we worked on is correct, versus for our purposes, we kind of hand wave it and say, well, we tried it with a few values, we got 3 to 4 to 5 reasonable results. That seems good enough. Questions about this exercise in this program? Sure.
Why do you have the digit sum declared as 0 equals 0?
Well, because the line that I was concerned about, and I said that Replit as a platform may paper over that for us, is because we're using it before we've initialized it to anything on line 20 currently. We say add the digit to the current sum. But if we hadn't initialized that digit sum, the C spec says that there's actually no guarantee what that value would have before we've done that initialization. So we'd be adding unknown, uninitialized value to the current digit. Now, Replit, as like a programmer safe haven that tries to minimize the amount of bugs you have to deal with, may wind up initializing all memory to 0. But in terms of good practice, there's no guarantee that digit sum would be 0 unless we explicitly set it to 0 ourselves. I have a feeling it would still work, but it would also be bad practice for me not to initialize it to 0. Yeah, well, there you have it. That's weird. But why would it be initialized to 2? Who knows? It's initialized to something for some reason. So in that case, that would have been a bug. If we hadn't initialized it, we get our value back of 14 once we've initialized it to 0. Eventually, you'll get pretty good at recognizing that I have a variable. I better make sure it gets initialized before it's on the right-hand side of an assignment operator. It better be initialized before I use it. There is no harm in excessive initialization. There's no harm in initializing all these values, even though they don't technically have the same issue of being used before they're initialized. That's not a bug, that's not wrong, that's not sloppy or anything to just explicitly initialize everything. The only variable in this example code that actually requires it would be digit sum, because we are using it, and if we're not careful, we're using it before it's been initialized.
You would have had a multiplication problem that caused error with that being 0 or not at all? Like the way you're declaring 0.
If it was a multiplication question versus like adding the digits, right. So it would have needed, for multiplication, you'd want it to initialize it to like 1 probably, I guess, versus 0. Otherwise, you're multiplying everything by 0, and then you just get 0 back out no matter what. But yeah, you do have to think about arithmetically what makes sense and initialize your variables accordingly. I don't want to belabor this example too much because it is, just another example. With regards to our number bases, we had this concept that we talked about, and I think the level of depth we provided is probably sufficient even on Friday, that decimal is just one example. It's actually base 10. Each digit is a power of 10. We also have an arbitrary base we can specify. The other most important one for us to be aware of as programmers is binary, is base 2. Where every digit in our value is either a 1 or a 0, and consequently we build up our number via successive powers of 2. So if in base 10, and I think I had it on a previous slide here, the number 4,125 can be represented as, let's do least significant to most significant instead. 5 times 10 to the 0 plus 2 times 10 to the 1, et cetera, or 5 plus 20 plus 100 plus 4,000. The same concept applies for all of our bases that we can have, including the binary base. And that's all that the binary representation, which actually is what gets stored in memory, is storing for us. It is storing successive powers of 2 via either a digit of 1 or a digit of 0. So for that same number, this is a different number. For a different number here, if we have this binary string representing 8 bits in memory, a single byte here, we can build up what the equivalent of that number would be by just following the same exact series of steps. This would be, again, from least significant on the right-hand side to most significant on the left-hand side. 0 times 2 to the 0. Again, anything to the 0th power is just 1. So 0 times 1, plus 0 times 2, plus 1 times 4, plus 1 times 8, plus 2 times 16, plus 2 times 32, plus 1 times 64, plus 0 times 128. Eventually, you'll have all your powers of 2 up to 32 to the 32 memorized. That number is corresponding to what's stored in memory 4 plus 8 plus 64, or 76. Let's take a quick moment. What would this number correspond to in base 10? Let's take a quick moment. This is not super critical in the sense that we need to be aware of binary. Everything is ultimately being stored in binary. You'll have a whole separate class where you'll learn digital logic and binary number systems, and you'll become extremely familiar with it over time. What would that number correspond to? I actually don't know the answer. So let's do it together. Least significant digit is 1. By the way, that's a very quick way to determine if a number is odd or even. If this thing is a 1, it must be odd. If it's a 0, it must be even, right? Because that's 2 to the 0. That's your 1. 1 plus 4 plus 8 is 13. Plus 16 is 29. Okay, thank you. Yes. So that number would be 29 in our base 10. And in fact, if we were to want to, we could very quickly refactor this same program to calculate all the decimal digits, all the binary digits, pardon me. Summing them up maybe wouldn't necessarily be that interesting, but if we wanted to calculate the binary digits, we could absolutely do that with our input value. Let's set current value to input value again so we can work on it without breaking the original input value. We were able to get the individual decimal digits by doing what 2 steps, right? We would do mod 10 to get the least significant digit, and then we would divide the value by 10 to kind of shift it over by 1, to go from 257 to 25. We can do the same exact thing with base 2, base 3, base 16, whatever base we want to choose here. Instead of doing mod 10, we would want to do mod what? Instead of dividing by 10, we'd want to divide by 2. And I would argue instead of doing it 3 times, if the value's in the range 0 to 512, 512 it'd be a lot easier if it was 511, to be honest. There we go. That's 512 is 2 to the 9. We'd have to do it 9 times. Again, maybe you're starting to see where having a 4 would make the code look a little bit cleaner, but copy and paste also works as long as we do it enough times. In this case, summing the digits may not be that impressive. Let's actually print the digits. We'll say the binary digits of this is R. Doesn't really matter. The binary digits are fine. And let's print them out. Grab the individual digit. In this case, we're not summing it up anymore. We're just printing it out. Let's add a space afterwards. You don't technically need to. It'll look fine without it. That's digit 1, 2, 3, Code's looking a little bad, but it'll work for 5, 6, 7, 8, 9. And let's add a little new line at the end so our code kind of cleans up nicely at the very end.
I know we're technically not that far into the class yet, but why not just set up a quick for while
That would be the correct way to do it. For now, this is a manual for the, you're right, but this is a little manual loop where we could also have a loop that checks if the value is currently 0, that means we're done, we don't have to do anymore, and that would be an if statement like we'll talk about, hopefully today. Where did the time go? We need to pick a value that's going to be easy for us to confirm is correct. Well, let's do, what did we say this was, 29? Is that correct? It's going to look a little different. Can someone tell me why? So the sum of the digits of 29 is 11, so that code's still there, that code's still correct. The binary digits of 29 are 1, 0, 1, 1, 1, 0, 0, 0, 0. What's the difference? Yeah, so, I would argue the convention is, most significant digit on the left and then least significant on the right. The way we wrote this program is we're doing the least significant digits first. So printf is kind of printing from left to right. So it's kind of reversed. It'd be a headache to refactor the code to get it to do it in the right order. We could do it, but the digits are correct. Those are the same binary digits, right? 1, 0, 1, 1, 1, with the rest being zeros, does give us that correct result. So mathematically, base 10, really nothing special. It's a natural thing for us to work with because we have our 10 fingers, and it's what we learned when we learned our own arithmetic along the way here. But binary, the actual underlying ones and zeros that both we use for storing our variables, as well as for the actual arithmetic operations that the computer is doing on those integer and other variables, it's really no different. There's more of them, I guess, right? So for the same value, we only needed 2 decimal digits, and in this case, we need upwards of 5 to store that same value, because each value is only storing a power of 2, which is less than a power of 10. But in terms of what we're doing for doing addition, for calculating individual digits, it's really the same. The only thing we changed here is mod 2 to grab the digit and divide by 2. And we had to do it a few more times because there was just more of those digits. But otherwise, the code was the same. If I said instead now do this as give me the base 13, just to pick some arbitrary number, we could absolutely do that as well. It would just be instead of mod 2, it would be mod 13 and divide by 13 along the way. I want us to make, yeah, go ahead, sure.
Is there a built-in function in C that will just automatically just invert the number?
Like go from 29 to 92, or to go from that binary range to that other binary range? Not the way we wrote this program. There is no way to just automatically do like a string reverse kind of function. We will have to be the ones who write that ourselves, but we'll be able to sort it out once we get to that point as well. The tricky part in terms of when we kind of introduce those things is by far the best way to do something like a reversal would be to store those as an array and then just iterate through that array in the opposite direction in kind of backwards order. When we get to that point, I think that'll make sense, but I just don't want us to get to that point yet. We'll get there soon enough. We could have also, if we wanted to, the other solution I think would have been fine, would have been instead of having a single variable called digit that we reused over and over and over again, we could have had a digit 1, digit 2, digit 3, digit 4, and then the only thing we would have changed would have been maybe a single printf at the very end that printed it in the opposite order, and that would have given us the equivalent of kind of writing it in the opposite direction. The trade-off is, how many variables you're using and keeping track of versus, how many lines of code you may have as well. A couple administrative notes before we jump into our next topic, which is branches. More generally speaking, control structures in C. We are going to start and talk more about like the relational and logical operators before we get into more of the complex if statements as well as case and switch statements. The lab is a little harder this time around. The reading assignment's a little bit longer. The coding practice shouldn't necessarily be any harder for you. So everything is kind of an extra week. And if you were to look in Canvas, my hope is that you would have seen that, but I didn't mention it. So I'm going to mention it again one more time right now. That if we go back to the schedule page, as well as the Canvas due dates for stuff here. We are here in week 3. We're now a couple days behind, but who cares? It's our own schedule we have to keep up with. Lab 3 already had the first day of, and tomorrow you'll have your first day of for section 2. Next week in lab is also still just lab 3. So the due date for lab 3 is not next Tuesday / next Thursday. It is a week from Tuesday, a week from Thursday. Same for the reading assignment as well. That's not me being like super nice. I mean, maybe it is, but it's, the material's kind of going to start to step up in difficulty here. You'll notice this happens a couple more times this semester because I just don't think, the assignment itself, it's going to be hard to finish it all in that 1 week. The other thing we have is what I think is a good time for a very early semester checkpoint. So next Wednesday, your coding practice and reading assignment are not due. The lab is not yet due, but what we will have is kind of our first checkpoint quiz. That's MQ Alpha. That's just a longer quiz. That's just a one-shot quiz, but it is still a quiz featuring a very similar nature of multiple choice questions on effectively what we have covered up through today in class on that quiz.
Will it be a simulation of the textbook or just the lecture slide that we've gone over?
It'll be both, and the questions, while I don't think they're any harder, there's more of them, they should look very familiar to you. They're of that exact nature of questions. It's not my goal to trick anyone in the class or to make you feel bad about your progress. It's a checkpoint. It's me checking in on you, seeing where you are individually in a way that the smaller quizzes don't really allow me to do. So please come to class next Wednesday. I'm speaking to those who are already here. Before we, given the minimum amount of time we have left, what I really want to talk about is our motivation for why this is a critical topic for us to cover. What our understanding allows us to do so far is to have variables that are stored in memory, to do scanf to read them in, to do printf to write them out, as well as various mechanisms to relate mathematical concepts into these expressions in our C programs. What we have, or what our programming knowledge allows us to have so far, doesn't really require a computer, right? The term computing tends to require that there be some data-driven decision-making that is happening versus what we have right now, at least in terms of that example we just finished, is really more just a calculator than it is a computer, and that's the distinction. A calculator, you type in numbers, you type in an operator, it gives you a result back out. We can write a lot of calculator-style programs, which is still necessary and good, but it's very limiting, as we've maybe already seen, in terms of what kind of programs we can have if we're not also doing not just a data flow of read input, do math, calculate output, but to also have some data-dependent decision-making where we're doing all those things still, where we're declaring variables, we're doing arithmetic on those variables, but at some or at multiple points in our program, we need to have some condition that's being checked based on those variables. And where we'll leave things off for today is this basic control structure. That's the basic if statement. The idea is that we have some way of determining if some value is true, and you really should be reading it out kind of explicitly like that. If some condition, then do something. And once we then have that in our programs, that allows us to do a lot more powerful stuff than what we currently have. And that's why Lab 3 is allowed to be a little bit harder than what Lab 2 was as well. And that's why you have a little bit more time to work on the reading assignment for that as well. Let's leave things here for today, and we'll dive right back in here on Friday.